And here we are, chapter 14, part 4. So we're going to kind of look conceptually at the chemical kinetics part in this video and look a little deeper at the relationships between temperature and rate, since we've talked about that in general terms, but not really mathematically or in any sort of way. So when we're talking about the speed of a reaction, looking more detailed than the original four factors that impact the reaction rate included like the physical state, the temperature, which we see here as well, the presence or absence of a catalyst, which we're kind of putting in its own category. And so this is looking at it like on the microscopic scale, like as if we could see the atoms. So these are the four things that impact the speed of a reaction. The temperature, which we know in general, higher the temperature, faster it goes, slower the temperature, slower it goes. How often the molecules collide, because we said that when two reactants need to react to make a product, they have to physically collide with each other. The more often these molecules are going to collide, the faster the reaction will go. An additional component, looking a little bit deeper, is when these molecules collide, they have to collide with the correct atoms touching. So what it means by the orientation of molecules. Part of that goes into play the VSEPR shapes, the linear, trigonoplanar, tetrahedral, trigonobipyramidal, octahedral, making sure that the two atoms that need to collide, like the atoms that are going to form a bond, it's actually physically possible for them to collide. So when two molecules collide, they don't necessarily react. They have to collide with the correct orientation, so that way the correct atoms are touching. And then the fourth thing, when the molecules collide, even if they are colliding in the correct orientation, where the chlorine collides with this molecule collides with the hydrogen of that molecule. If those two atoms collide, they have to collide with enough energy in order for this reaction to happen. So if they just slowly bonk, and then they're just going to bounce off of each other and continue. They're not going to react. They need to have at least a minimum amount of energy, which is called the activation energy. So again, I mentioned earlier in chapter 14 that as temperature increases, the rate goes faster. I mentioned some things like we use refrigerators to slow down the chemical reactions that occur in food as it spoils. Refrigerators make it cold, so the reaction slows down. I mentioned putting batteries in the fridge or the freezer to slow those down. Okay, so just in general terms. But the part of the reaction that temperature impacts, it's not the rate law. So it doesn't change if something's first order, second order, or zero order. The temperature doesn't change that. Okay. The only thing that the temperature changes is the rate constant. Lowercase k is temperature dependent, which I did mention when we were talking about the rate constant and calculating with it in the last couple of videos. So if we have something we have a rate law. This is made up. Okay. I don't know the kinetics of this reaction. So I'm saying in this rate law, in my pretend rate law, that hydrogen is first order, oxygen is second order. The overall reaction is third order. So if I did this reaction at 25 degrees Celsius, and that's where I got this rate law, and then I redid the reaction at 85 degrees Celsius, so a completely different temperature. The rate law itself, these symbols are going to look the same. Oxygen will still be second order. Hydrogen will still be first order. The thing that will differ is the value of K. K will have the same units, but the number will change. At the higher temperature, the number is going to be bigger because the rate is going to be, well, I should draw the arrow the other direction. The rate's going to increase. And if hydrogen and oxygen are staying the same, then K has to be the thing that increases as well. So the graph at the bottom with the red line is just showing you 4 different experiments for the same reaction that were done at 4 different temperatures. On the x-axis shows the temperatures, and on the y-axis it shows the rate constant. So we can see that as the temperature increased, so did the rate constant. It's not necessarily linear, which is why these values have to be determined experimentally. If you need to know the rate constant, you have to do the experiment. Well, we're going to see how we can calculate it here in a little bit, actually. But at least the first one has to be done experimentally. So the collision model, again, we're looking at conceptually when these molecules are reactants and they're going to collide to make products? What all has to happen? Okay, so I said they have to physically collide with each other. And in this scenario, this is reactant 1. I'm going to write R1. And this is reactant 2, R2. Okay. And then this is product 1. And this is product 2. Okay. So for my two reactants, they have to physically collide. Well, if we look at our products, they need to physically collide so that way the green atom of reactant 1 and the green atom of reactant 2 are what collide, because those are the two atoms that have to form a bond. So in order for them to form a bond, they have to be pushed together so they can then form that bond. So when reactant 1 and reactant 2 were floating around in the beaker, when they collide, if the green atom collides with the red atom, this reaction doesn't happen. If the green atom collides with the blue atom, this reaction doesn't happen. If the green atom collides with the green atom, ooh, we're talking, we could have a reaction, but the additional thing is they have to collide with enough energy for the two atoms to smush together enough for that bond to be formed. And then when that happens, the bond here is going to break. So we'll be forming a bond there and breaking a bond here. Now, we can see that for a little bit of time, there's going to be this molecule that's neither a reactant or a product. It's when the green bond has formed, but before the green-blue, when the green-green bond has formed, and before the green-blue bond has broken. And we're going to put some words to that here in a second. So this is just showing that the collision model is just saying, well, we have to have two things that happen. The molecules have to collide with the correct orientation, which means the correct atoms are the ones colliding. And when they collide in the correct orientation, they have to have enough energy. That's why reactions aren't all instantaneous. It doesn't happen immediately. Maybe it's really difficult for the two atoms to be able to collide because of the shape of the molecule. Okay. So now we're going to focus on the energy thing. We're not so much going to look at the orientation. You need to know that the orientations have to be correct, but we're not going to go down into modeling atoms and looking at that. What we're going to focus on now is the energy component. They have to collide with enough energy, right? So that a minimum amount of energy, the least amount of energy they have to have when they collide in order for the reaction to happen is called the activation energy. It's the amount of energy that activates the reaction. And it's represented by the capital letter E with a subscript A. E for energy, A for activation. Okay. So every single textbook and explanation I've ever seen of activation energy uses golfing as an example. Now for me, I am not someone who like goes to golf courses and golfs. That's just not me. I don't know what it is. That's just not for me. I've done it a couple of times, whatever, but I'll go putt-putting. Okay. So for my example, I'm going to think about putt-putt golf. So the putt-putt golf courses, there's usually one that you have to hit it. There's like a hill. And if you can get it up the hill just right, the ball will then roll directly into the hole. If you hit it too softly, the ball will roll back to you, and at least in my case, go behind me from where I started, so it goes further away than it originally started. And if you hit it too hard, it's just going to fly off the top of that hill and just go off into someone else's court or area, or hit a windmill or something. I don't know. But so there's kind of this like sweet spot. Okay, so thinking of that analogy, that hill, that sweet spot is the activation energy. That's the softest you can hit the golf ball, but have it go over the hill. Okay, so it's enough to get over the hill, but it's any less, it wouldn't have made it over the hill. So it's the minimum amount. Okay, so with this analogy, that's the molecules colliding at exactly the activation energy. The reaction goes on to the products. If the molecules collide with less energy, so when they collide, it's less than that, they don't move on, they don't go over the hill to the other side. Instead, they go back to the beginning, which means they're still the reactant molecules, they did not react. So if two molecules collide with less than the activation energy, the reaction doesn't happen. Now, if the molecules collide with more energy than the activation energy, so they didn't just barely get over the hill, they flew over the hill because they collided with too much energy. Well, that's when it doesn't track with the golf thing, because as long as they hit with enough energy to get over the hill, you make your product. So if you hit it, if the molecules collide with too much energy, no problem, we made our products. Okay, so it's really, are you less than the activation energy? No reaction. Are you at or above the activation energy? The reaction goes. Okay, so that activation energy is an important thing. This graph is called the reaction coordinate diagram, and this is one that we're going to see in Gen Chem 2, obviously, that's where you are right now, but you're also going to see these in organic chemistry for those of you that's the next step after Gen Chem 2. So reaction coordinate diagrams give us an idea of the energy necessary for a reaction to go from the beginning to the end. So in this reaction, this would be my reactants, and this is how much energy they have. These are my products. Okay. And then the red line, the y-axis is showing the amount of energy. So the lower the line, the less amount of energy it has. The higher the line, the higher energy it has. And then the x-axis says reaction pathway, which is kind of a made-up thing. It's like as if every step along the reaction I took one step over. It's just keeping track of, okay, the beginning of the reaction here, and then the next thing happens here, and the next thing happens here, and the next thing happens here. It's just the step by step from the beginning of the reaction. That's each place. Okay, so these are always going to make hills. Okay, and the activation energy is defined as the highest point in the hill. Well, it's the difference between the highest point in the hill and where you started. So how much energy does it take that golf ball to get over the hill? Well, that's the difference between where you start and the highest point, and that's the activation energy. Okay, the higher the hill, so if I had a reaction coordinate diagram that looked like that, little hill, and then I have another one with the same scale that looks like that, I can eyeball these two and tell by looking at it which one has a higher activation energy without doing any math. The taller the hill, the higher activation energy. So what do you think how that corresponds to how fast or slow a reaction happens? High hill means the molecules have to have a lot of energy. Well, that's not going to happen very often. So the higher the activation energy, the slower the reaction is. This one will happen faster than this one because it has a smaller hill. Thinking back on the putt-putt golf thing, more often when you hit the golf ball, you're going to be able to get over this hill more times than you would be able to get over this hill, okay? Because you can hit it less hard to get over that hill. So the reaction coordinate diagrams kind of give you a glimpse of a lot of things about this reaction. Okay, so if this is reactants and this is products, at the top of the hill, that's what's called the activated complex. That's remember how back here when we had the two greens were stuck together, but that was before the green and the blue had broken. There's kind of the in-between, the not finished yet thing. That's called the activated complex. That's when it's halfway reactants, halfway products kind of thing. Okay, that happens at the top of the hill. So we're gonna call that the transition state. Okay, that's the term that we're going to use, which is when everything's smushed together. It hasn't yet broken apart. The reactants are there, the products are there, but they're all smushed together. Okay, so it's the not reactant, not products, and it's just in the middle phase. It hasn't finished. Okay, so at the transition state, so the transition state is the location of it, but that's what I'm going to the term that we're going to use. The molecule itself is called the activated complex. Okay, so we talked about how the activation energy is the distance between starting point and highest point of the hill. So that looks at temperature that looks at activation energy, the energy that they have. So what we're going to look at here is kind of the temperature and how that relates with these reactions. So we said in general, the higher the temperature, the faster the reactions go. And the relationship with that has to do with the activation energy. So when temperatures are higher, the molecules move faster, which means they have higher kinetic energy. So that is an energy value. Higher temperature, more energy. The more energy they have, because they're zipping around faster in the beaker. When they collide with each other, they're going to have more energy when they collide if they're moving faster. Okay, so that means at a higher temperature, more collisions are going to result in meeting the minimum, like the activation energy, or higher. So that's why increasing the temperature is going to make the reaction go faster, because more of the collisions at a high temperature, the molecules are moving faster. So when they collide, more of them will have enough energy to get over the hill. So that dotted line in this graph is showing the activation energy for this specific reaction that they were looking at. And they did the reaction at two temperatures, the blue curve is showing at a lower temperature and the red curve is showing at a higher temperature. And what these curves are just showing is they broke down the molecules into how much energy they had. Okay, so everything that's from here over are the molecules that would have enough energy when they collide to force products. Like they would go over the hill. They had enough energy to meet the activation energy. Well, you can see with the red curve, there's more of those. If we were to, for those of you that are familiar with calculus, calculate the area under the curve, there's a bigger area between here and the red line than here to the blue line. Okay, so more molecules will get over the hill at a higher temperature. Okay. Now, to be fair, at a certain temperature, not all molecules have the same energy, but in general, higher the temperature, all molecules have more energy. Okay. So the Maxwell-Boltzmann distribution was trying to put that. There was a way to put that into numbers. Okay. And Arrhenius took that relationship with the numbers and the graphs that we have seen. This was the first Arrhenius equation. Okay, now some of these symbols are hopefully familiar. Lowercase k is the rate constant. E to the power of is like the inverse of natural log. Lowercase e is not a variable. EA is activation energy. T is temperature. R is 8.314 joules per mole Kelvin. It's a constant. Okay. Now, the issue with this first equation was the capital letter A, which is just another constant. But unlike R, which is basically it's the gas law constant, just converted its units. Capital letter A is different for different reactions. So that's not convenient. We don't always know what that is. There's not a table to look that up. So instead, the equation down here in the box is the version of the Arrhenius equation, because he's the scientist that put all these pieces together. It's the version of the Arrhenius equation that lets us predict the rate constant at a specific temperature for a reaction. So what it did was we did a scenario 1 and scenario 2 to let us cancel out the value A. Okay. So in this equation, K1 and K2 are rate constants. And so 1 and 2 would be like, well, I did the reaction the first time and it was at 25 degrees Celsius. K1 was the rate constant at 25 degrees Celsius. K2 is then, okay, I redid the reaction at 85 degrees Celsius. So K2 is the rate constant at 85 degrees Celsius. The T's are temperatures, and obviously they have 1s and 2s next to them as well, so those have to match with the rate constants. Those have to be in the unit Kelvin. Okay, T1 and T2 both have to be in Kelvin. R is 8.314 joules per mole Kelvin, and then EA is the activation energy. So this gets us, well, we can use this one of two ways. We can now solve for the activation energy if I did the experiment twice. Or if I do the experiment once, I can use this equation to predict what the rate constant would be in a theoretical second situation. Now, the R value, 8.314 joules per mole Kelvin, that is going to what we have to use to determine what units we're allowed to use. So I already said temperature has to be in Kelvin. And so based on those units, that means activation energy needs to be in joules per mole. The rate constants, their units aren't going to matter because look, it's a ratio. And they're going to have the same units because it's the same reaction. So the rate constant units will cancel themselves out. So things we have to watch out for. Temperatures have to be in Kelvin. The activation energy has to be in joules per mole. 8.314 is a given value. We'll have the units joules per mole Kelvin given. And then it's just making sure that you match up K1 and T1 and K2 and T2 to the correct places. So you will be given this equation. You will be given the R value as a constant. Let's see if we can use that information to solve something. So this was just showing how if I graphed it, I could get these values. I care less about that than I should. Okay, so let's try this. The activation energy for a process is 75.5 kilojoules per mole, and the reaction was measured to have a rate constant of 2.75 times 10 to the negative 2 inverse seconds at 20.0 degrees Celsius. What would the rate constant of this reaction be at 60.0 degrees Celsius? So we've done a lot of problems in chapter 14 so far. We only have one equation that has activation energy in it, and that's this Arrhenius equation. So that's your key word telling you that you're using the Arrhenius equation we just saw. Okay, so that's our Arrhenius equation. And we know every time we use this Arrhenius equation, R is 8.314 joules per mole Kelvin. So let's see if we can take the numbers from the problem and decide what variables those should be, and then we'll look at putting them into the equation. So, to starting at the top, the activation energy for the process is 75.5 kilojoules per mole. Well, activation energy, that symbol is EA. So that number is EA. The reaction was measured to have a rate constant. Well, that's rate constant symbol is lowercase k. So I'm going to call this K1 because it's the first one mentioned. Is 2.75 times 10 to the negative 2 inverse seconds at 20 degrees Celsius. Well, T, that's a temperature, and I'm going to call that T1 because that matches with the K1. The question is then asking, what would the rate constant, so we don't know the other rate constant, of this reaction be at 60 degrees Celsius? Okay, so before we plop numbers in, let's look at our units and make sure everything's good to go before we put our numbers in. So R, it has the units joules per mole Kelvin. So let's look at all the other units. EA is in kilojoules per mole. Crap, that doesn't match. That needs to be in joules per mole. So I'm going to multiply it by 1,000 to convert kilojoules to joules. There are 1,000 joules in 1 kilojoule. The rate constant, 2.75 times 10 to the negative 2 inverse seconds. That's not going to matter because the other rate constant will cancel, or we'll have that unit in order to cancel it out. What do you think about the temperatures in degrees Celsius? Are those good to go? No, they have to be in Kelvin because R has Kelvin in it. So I'm going to add 273.15 to convert this from degrees Celsius to Kelvin. And now my numbers are ready to go. So since I'm out of space here, I'm going to go to the next slide, and I'm just going to take this equation and these variables and start putting them into the equation. So natural log K1, which we said was 2.75 times 10 to the negative 2 inverse seconds, over K2, which we don't know, so I'm just going to write the symbol K2, is equal to EA, which we said was 75,500 joules per mole, divided by R, which is 8.314 joules per mole Kelvin. And then in parentheses, 1 divided by T2, which we said was 333.15 Kelvin, minus 1 divided by T1, which was 293.15 Kelvin. So this may look ugly, but everything on the right, I can use my calculator and do the math and get one number for everything on the right. Okay, I do have to do parentheses first, right? Because that's how math works. We have to do parentheses first. So first I'm going to have to do the 1 divided by 333.15 minus 1 divided by 293.15. Take that number times 75,500 divided by 8.314. Okay, so what I'm going to do is I'm not going to do that step by step by step. Instead, I'm going to say, well, I've not touched the left-hand side yet, so I'm just rewriting that. And when I did all the math on the right-hand side, I got negative 3.719351354354. So 454. And if we look at units, cancel. This is 1 divided by Kelvin would be the units here. And over here, this is 1 divided by 1 divided by Kelvin, which is Kelvin to the negative 1 to the negative 1. So the Kelvins are going to cancel is what's going to happen. So this number truly is unitless. Now I'm trying to solve for K2. Right now, things look a bit of a mess. I've got a natural log that I need to get rid of before I can break this apart. Or I can use log rules and say that this is equal to natural log of 2.75 times 10 to the negative 2 inverse seconds minus natural log of K2. I could break that down using log rules and then rearrange. I'm going to just leave it like this. So I've got this whole thing. Earlier in the chapter, when we used natural log, we said the inverse of natural log was e to the power of. So what I can do is take e to the power of this side, that cancels, e to the power of that side and get a number, and then just do algebra. So from there, I'm just doing algebra, and what I got was 1.13 was the number that I got when I did all this math. Okay, Units. Everything on the right is gone. The only unit left is seconds negative 1. So these are not quick. These are time consuming. The Arrhenius equation just is. There's a lot of variables. There's a lot of things going on. So there's a lot of places that it's really easy to make a mistake with math. Okay. No, if you went through all this and you got a different number than me, you just need to let me know so I can walk you through all of the steps. But a way to double check that you didn't, to hopefully try to catch it if you did something really silly with your math. What we said before we got to the math here was that higher the temperature, faster the rate, and that the rate constant was the thing that changes. So that means higher temperature, higher rate constant. Lower temperature should have a lower rate constant. So let's go back and see if the math worked out where that trend follows. So our answer was 1.13 for K2. Well, K1 was 2.75 times 10 to the negative 2, so 0.0275. That was the rate constant at 20 degrees Celsius. So the rate constant at 60 degrees Celsius, it's a higher temperature, so shouldn't K2 be bigger? Well, 1.13 is bigger. So I can't promise that I didn't make a mistake with my math. Like if this was a test question and you're trying to double check that you didn't do something wrong, I did do this problem right, just so you know. But if you were, I'm thinking of in your shoes on a question that you don't know the right answer. You can check this trend. If you were looking at a higher temperature, but you got a smaller number for your rate constant than where you started, you did your math wrong. Okay. So this equation will be given to you. The constant will be given to you. It's your job to get them in the correct units, to plug them in and solve.